think as we were, discussing with Curatia the other day, we're talking about these issues, and I think she identified how important it is to try and improve the understanding on this. So what I'm going to share with you this morning is basically an outline of the work that we do as part of our work with FuseNet. You might be aware that FuseNet covers about 5 countries in Southern Africa. And out of those, we've got food security experts who are working with the national people in the national partners. And I'm also working closely, being seconded to FNR, with SADC, Food, Agriculture, and Natural Resources. I see Ms. Skinner here on the call. Welcome, hello, and all the other colleagues as well. So we are working to try and use this climate information to identify in advance the times when we are going to expect droughts and the drought impacts on the populations. So as part of the work that we do, FuseNet regularly undertakes analysis of the different forecasts that are available from different centers. So we're going to talk about these during the next hour, 30 minutes to an hour or so. And then we'll also share with you some of the products that we have put together and we regularly analyze to monitor the progress of the season, as well as how to interpret both the climate forecasts as well as the drought monitoring, seasonal monitoring, actually, I meant to say data. So I'd like to say that at the beginning of this season, of this presentation, that please feel free to, I think, stop me if you've got any questions. It might be a little bit technical. I'll try and really lay it out as clearly as I can. There's a saying, Einstein is reputed to have said that if you can't explain something simply, you don't understand it well. So I think this will be the big test for me, whether I also understand this climate forecast and drought information. Right, so as I mentioned, this is based on training materials that we have developed for internal FuseNet training of our food security experts. But I'm sharing this with you so that you can kind of get an appreciation also of the same data that we work with within FuseNet. So this is basically a FuseNet experience, if you want to put it that way. So we start off by looking at the different type of forecasts that we generally use in FuseNet. I think we can divide it into 4 types of forecasts. Some of these overlap, but probably the most common that you see is what we call the probabilistic forecasts. So with a probabilistic forecast, we're basically saying, what is the probability that we're going to get so much X amount of rainfall, or that rainfall will be within a particular range? And this is what you typically get from SACOF, is what you typically see also from the international centers.
Can you please share screen? Can you please share your screen? I don't see. Thank you.
Apologies. Okay. It says I'm sharing my screen. Oh, okay. No, I'm not. Okay. Is this what you call the born before technology issue? We're not born with PowerPoint, But anyway, thanks for highlighting that. Can you see my screen now?
Yes, we can, Temuka.
Yes.
Okay, great. Thank you so much. Okay. So I think just to get you catch up, you haven't missed much, because I think most of what I was saying were on the first slide, which is just basically the title slide. But thank you for highlighting that. I need to share my screen. So I was mentioning that there's 4 different types of forecasts that we look at. We've got our probabilistic forecasts, which give us a probability of rainfall being in a specific interval or range. We also have we also have dynamical forecasts. So I was saying that there's overlap between these, because dynamical forecasts can be probabilistic, and statistical forecasts can also be probabilistic. So I would say that really the distinction would be between dynamical and statistical forecast, because dynamical forecasts tend to use physics of the atmosphere and the oceans and the the land surface to predict how air particles will behave over the next few hours to the next few months. And if we are looking also at the climate change models, then even over the next few years and decades. But all it's saying is that they're using equations to see that, to estimate that, when air is heated by a certain amount, it's going to move to a certain point, and then you're going to have pressure here, and it's going to push that pressure is going to push that air particle from point A to point B, and so on. So, but we don't want to get too much into that detail. I want to distinguish it with a statistical forecast, because with our statistical forecasts, these are now based on historical relationships between a variable and between a predictor and a predictant. So, an example, we noticed that I'll try and give you a non-climate example, but we might notice that each time, okay, I'll stick it to climate. They say stay in your lane, right? So each time we get low temperatures on a particular day, maybe the next day we're going to have lower level of activity, or maybe we'll be shadowing as an example. So you are basically using your temperature the day before to predict what the activity is going to be the following day. Like I was saying, I'm trying to use a non-climate example, but it ended up having some climate in it, just to show you that that's the statistical forecast. So if we take those observations over time, like over 20, 30 observations or 20, 30 years or something, we can predict that each time the temperature drops a certain amount, then we're going to have a certain activity in the following day. But bringing it to climate specifically, and this is where this example is here, we found that sea surface temperatures in particular regions of the ocean tend to be, so the temperature of the oceans in a particular area tend to be well related with rainfall in other regions. One good example of this is the El Nino and La Nina, where we find that when we have got La Nina, which is related to temperature in the Pacific Ocean, we tend to have above average rainfall in Southern Africa. And so we can take 30 years of temperatures over the Pacific Ocean and take 30 years of rainfall over Southern Africa, and we can actually do a regression between these two and come up with statistical forecast. So that's the difference. Statistical, you're looking at historical observations. Dynamical forecast, you're looking at equations and physics to see the principles by which different air particles, I would say, develop over time to produce certain weather events. Then the fourth type is what we call the ensemble forecast. And with the ensemble forecast now, you are running your dynamical forecast many times using, I'm basically just reading here, using slightly different initial conditions. So to determine whether your forecast is consistent in what it's saying when we vary the conditions a little bit. And the reason for this is that when we run our dynamical forecast, we have to assume that we're starting at a particular point in terms of the condition of the variables. Like we say that our temperature starts off being 30 degrees over Gaborone, and our humidity is so much. And we're assuming when we take it from that particular point, and then we now project over the next 5 days, what will our temperature then be like 5 days from now? But we're assuming that we know exactly what the temperature in Gaborone is. But what if it's not 30 degrees? What if it's 30.5 degrees, but we don't have the precise, we don't have the ability to measure that precisely. So in order, what the science has found is that even a slight variation in that, in how well you have measured your initial conditions, where you are starting the forecast from, a slight variation can cause a large difference later on. So we run the forecast many times using slightly different initial conditions. Maybe we're going to start with using the example I gave just now. We're starting with maybe 30 degrees, and then we're going to run the forecast again, assuming we're starting at 30.1 degrees, run the forecast again, assuming we're starting at 30.2 degrees. And what happens when you do that is that sometimes the forecast is going to give you almost similar results, like 5 days. I'm looking at a 5-day forecast as an example. And in that case, you've got some confidence in your forecast, right? But sometimes if you change even by a little bit, it's going to make huge changes. And then you are going to say, no, we're not very confident in this forecast. We don't have much confidence in what this forecast is telling us. And so you have to put less weight on it. And all this is to try and also explain why we, the climate scientists don't just tell you that, you know what, this year rainfall is going to be 20% of normal, or we're going to have a really bad drought this year, or everything is just going to be great. Because we don't know, simply because they call it chaos, and there's so much variability that can occur over those next, in this case, for climate, we're looking at about 3 to 6 months. So there's so much that can happen within that. And that's one of the reasons why we run the ensemble forecast, which also, these ensemble forecasts also help us to then come up with a probabilistic forecast, especially for dynamical forecasts, because it will tell us what our probability of rainfall being a certain above normal or below normal and so on. So having given that, I hope that was clear. And I passed the Einstein test that hopefully I was able to explain it in an understandable way. But so what we're going to talk about is also how the forecasts are communicated. I'm going to focus on the probabilistic forecasts and just touch on some of the, especially the dynamical as well as the ensemble. And then I'll also talk about how to interpret some of these forecasts as well. Right. Okay, we're skipping the categorical. I think I mentioned in passing already what the probabilistic forecast is, but it assigns the likelihood that, you know, a rainfall is going to be, or temperature, or particular parameter, okay, is going to be within a particular range or a particular amount. And this is the example, an example here which tries and explain how the probabilistic forecast works. So this is under, this example is showing us under normal conditions. And this is, you typically see your forecast having 3 figures, like 33, 33, 33. You don't usually see that in Southern Africa, but some regions do produce a forecast which looks like this. And what it's saying is that basically it looks at rainfall for the past, let's say 10 years, right? And last 30 years, I'm sorry. And then it measures how much rainfall we had for each of those last 30 years. And so from there, we're going to estimate, okay, so in year 1, we had this amount of rainfall. That's about 20 millimeters. Another 20 millimeters year 2, 20 millimeters year 3, 20 millimeters year 4. And then year 5, we had this amount of rainfall, years 5 to 10. And so these are 30 dots. Each of them represents a rainfall event, or the amount accumulated over a rainfall season. And what we do is that we now divide it into what we call terciles. So tercile is 1/3 of all the rainfall observations you have made. We can call them your distribution. And so with that, you can basically see that 30%, 33% of the time, my rainfall will be between 0 and 100 millimeters, right? Another 1/3, so that's our below normal. Another 1/3 of the time, rainfall will be between 100 and 200 millimeters. Remember, we've got 10 observations here out of the last 30 years, and another 10 observations here in the last 30 years. So, and then in the above normal now, 1/3 of the time, we also had rainfall falling between 200 millimeters and 400 millimeters, right? So we used all this information to come up with a distribution a probability, what we call a probability distribution function, if you are familiar with statistics. And it basically models how if we throw, or if we guess at random amount of rainfall that we can get, it should fall within any of these, and we should get them in equal amounts. If we guess 30 times, we will get 10 rainfall events here, 10 rainfall events, 10 rainfall events there. So this is what we call our climatology. That's what we typically expect under normal conditions, right? But now what happens is that we might get a shift in a particular year, maybe because we've got an El Nino, or in this case, it would be a La Nina, perhaps, because La Nina is what typically affects, causes above normal rains. So when we have observed or done our statistical modeling, or we've done our dynamical forecast, well, our forecast is going to tell us that no, rainfall is now going, our rainfall distribution is going to shift. So it's going to look more like a shift to the right. And so we're going to now have a higher likelihood of rainfall being above normal. And so based on this forecast, I would say that our probabilistic forecast, we now have 43% chance of above normal. Remember, before it was 33 in each case. Now we've got 43% of above normal, 37% chance of normal, and 20% chance of below normal. And we can see it from this because based on our model run, the amount of rain, the likelihood of getting below normal rainfall has decreased, right? We are more likely now to get rainfall in the above normal category. So, okay, just to mention, because it's on the slide and you might be wondering, the categorical or deterministic forecast would then be saying that, so this would be like the most likely, perhaps, we're expecting that rainfall will be 280 millimeters. So what you'll find is that our models actually have got the ability to come up with a specific number, because I know people normally ask, just tell me, is it going to rain or not rain? So I can use a model to tell you that information, but as you can see from the graph, there is so much variability that I would not be an honest broker if I to give you a specific number like 280 millimeters. So that's why we tend to express it as a probabilistic forecast. So we kind of use present the information in the most responsible way, which gives you an indication that there is a chance of different outcomes occurring. And that's why our climate scientists tend to prefer the probabilistic forecasts. So we've got an example of a probabilistic forecast here. This was for March to May 2021. This is typically, I think, the Eastern Africa, which is more affected by rainfall during this period. But so it's showing, this is from what we call the North American Multi-Model Ensemble, which is one of the forecasts that FuseNet uses quite a bit. We do look at different forecasts altogether. But so let me try and explain what this forecast is saying. So remember how we're talking about our terciles and our probabilities. We've got a certain probability that rainfall will be below normal. That's expressed by this part of the legend. We've got the probability that rainfall will be normal, and we've got likelihood that rainfall will be above normal. And so the way that this forecast has been designed is that it gives you the most likely tercile. So the tercile with the highest probability is the one which is shown on this map. Right? So for example, this was, okay, I said March to May. It would have been interesting probably I'm sure you'd have been more interested to know what October to December 2022 is like, or January to March 2023 is like. I think we'll come to that, but this is more in terms of, for now, trying to share with you the concepts. So let's try and interpret this graphic. So what we're seeing, let's say we'll pick an area, let's say central Mozambique here. We can see these medium green colors. I think it's in this range here, 40 to 50. So what this forecast is telling us is that in central Angola, I think this is the Tet area, the highest likelihood is that rainfall will be 40 to 50% chance. There's a 40 to 50% chance that rainfall will be above normal. Okay. There's also a chance that rainfall will be normal, and there's another chance that rainfall will be below normal. But for this graph, we're not so concerned with them because this is only showing us the highest likelihood. Okay. So we are focusing more on that highest likelihood because we don't want to, you need to choose a number and do something, right? Let's pick a different area. We've got here southern central DRC, which is part of the SADC region as well. And what we're seeing here is some of these, they are quite light, but we've got colors in the maybe 36, up to 36%. So there's maybe up to 36% chance of below normal rainfall. This is the highest likelihood we're getting. But keep in mind that 36 is very close to our climatology of 33. So even though we've got like a 36% chance that rainfall is below normal, there's almost an equal chance that rainfall maybe is below normal, is above normal or normal. So because there's such a low probability, our highest probability is so low, you know, we don't express much confidence in a forecast like this, right? So you might ask, what about the white areas? There's a lot of white areas in this map, and what we get from there is that based on our models, we did not find sufficient confidence to express any particular outcome, whether it's below normal or above normal. And this is actually a very common occurrence. I know that, you know, we tend to want to provide some advisory based on what so sometimes the models won't tell us really where it's, what is most likely. So then we need to now have what we call expert judgment in some circles. You need to have a human being come in and say, okay, based on what I know about this area and the indications that I'm seeing, even though the models are not saying anything specific, but I would say that it's most likely that, you know, we'll have below normal rainfall or above normal rainfall in this area. So we're going to end up putting a value there based on now also our human intuition. And that's not necessarily a bad thing, because you remember that also computers, these models, you noticed from this that there's a lot of uncertainty in these models. But if you're trying to provide advisory to somebody, you need to tell them what you think is most likely. Yeah. So I think that, okay, so now compared with the categorical forecast example here, and in this particular case, is the same forecast as this one, but it's expressed differently. And we're saying this is the most likely outcome based on the model. So you get like an average of all these different forecasts, potential forecast outcomes, and you come up with a particular number. So we're saying that maybe over southeastern Zimbabwe, we expect an average of about between 1 and 2 millimeters per day as our, so they express this as millimeters per day, but it's really still it's a single number. It's a categorical forecast. We're saying this is the most likely based on the forecast. So that has to be also interpreted with some, I guess, responsibility on behalf of the person who is doing the interpretation of the forecast. But this, because of the uncertainty, as I've explained, this tends to be the most popular way of presenting, because it's trying to indicate not only what's expected in terms of a range, is it above normal, is it below normal, is it normal, rainfall expected, but also the confidence we have in that particular outcome, right? So this is more the sort of thing that we see with our forecast in Southern Africa. This is an example of a SACOF output, and we'll be seeing probably something like this as well within the next couple of weeks. I believe 24 to 26 August is the date of SACOF when we will be getting the official forecast for Southern Africa. And so what do these three numbers mean? We can see we've got the 35, a 40, and the 25 there. Did I explain it? Yeah. Okay. And so let's look at the explanation here. Right. So we start with an example here. Okay. So these three numbers, we've got a 25 here, a 40 here, and a 35. I'm referring to the one which is circled in red. And what this basically means is that we look, the top number is the probability of being above average or above normal. The middle number is the probability of being in the middle. Remember, we said we broke up our distribution into thirds. The top, so if we're looking at 30 years, the 10 years when we had the highest rainfall, what was the amount of rainfall in each of those 10 highest years? We've got the middle range, which is our average rainfall, and then we've got our lowest range, our lowest 10 observations out of 30 years. What is our lowest 10 years? So based on this, we can say that we've got a 25% of rainfall being in the above average. So that's the lowest of these three. We've got a 40% chance of rainfall being in the average range. We've got a 35% chance of rainfall being in the below average range. Okay, so it's more, what is most likely is that we are going to get normal rainfall. And then the second most likely is below normal rainfall. And the third most likely, the least likely, is above normal. So SADC has cleverly found a way of presenting this even graphically by associating the colors used to represent the probabilities with the different probabilities themselves. So typically yellow is when we've got this scenario where normal is most likely, below normal is the second most likely, and above normal is the least likely, right? And then for blue, for cyan, I think this color is called cyan or light blue, if you like. We've got, again, a situation in which 40, the middle range is the most likely, but now it's been switched around. Now the above normal is the second most likely, and the below normal is the least likely. And so we see that, we typically hear people say that, okay, this year, and I think we're probably going to get this. I'm not preempting SACOF, and please note, this is not the focus for this year. I wouldn't want to hear anyone say Tamuka gave us the focus for this year, because this is OND 2013, right? But we're probably going to hear statements like, for a particular region, we're expecting normal to above normal rainfall, or we're expecting normal to below normal rainfall. What do we mean when we say that? What we do is that we take the highest two numbers from this probability, and we add them up, and then we take that as our normal as the highest. Our highest is the one which is assigned the first place in the title, and then the second highest is the one which is assigned the second place. So like this would be normal to below normal, right? Because 40 is the highest, 35 is the second highest. This would be normal to above normal, right? So I think this is illustrated as well in the graphic there. Right. I think that covers it. Also, so when the dark blue normally is when we're expecting normal rainfall. I mean, above normal rainfall is our most likely outcome, and they call this as above normal to normal, but you can also just say above normal because your normal will usually always be your second most likely. We don't have the ability to distinguish between above normal as our most likely and then below normal as our second most likely. So the second one can be, you don't have to use it, but just I think for the sake of expressing the uncertainty, it tends to be expressed this way, above normal to normal. Okay. Maybe I should stop here and ask if there are any questions for proceeding. I hear silence, so that either means everyone understands or I've been left all by myself and I'm no longer in the meeting. But I think I'm still seeing everyone. So yeah, we'll continue with that. Okay. So I think this has already been explained. It's basically the probability that rainfall will be each test. But I was mentioning, some regions, this is for the Caribbean. You see a bit of this as well. 33. What they're basically saying there is that there's the other way of putting this is equal chances of each outcome. So there's always an interest in terms of, so how do you interpret or how do you use this information? Because I think this is probably something that is of considerable interest for people who are in the early action. Given that, so I think there's, based on what I've heard, and this is my personal opinion, based on experience that I've had over the last few years, it seems like there's kind of two ways of taking this information, being that it's a range. I think the one approach is to just take the most likely outcome and then build your plans around that. So for example, in this particular case, if we're expecting normal to above normal, you can just take, one approach is just to assume that, we're assuming that we're going to have normal rainfall. And what does normal rainfall look like? You now have to start looking at the climatology as well, better understand the climate of the area. How much rainfall is normal rainfall? If you want to go even deeper in depth, do you typically have dry spells during that period? When does rainfall normally start and end during a normal rainfall season? And then you kind of build your responses and your actions around that. Right. Another option is to kind of weight, WEIGHT, weight. Weight your responses according to the probabilities expressed in the forecast. So for example, let's say you're a farmer and you get a forecast of above or normal to below normal. So again, normal is your most likely outcome there, but there's a good chance that you might get below normal rainfall. So what would you do then? If you are planting, you might then decide to spread your seed according to maybe planting a larger portion to maybe high yielding, especially because it also depends what is normal in your area that you grow your crops or that you are responding to. I know there's in the FNSWG, we've got international organizations, we've got NGOs that support different initiatives and so on. So if you also have to understand what is normal in that area that is normal usually high rainfall or slow rainfall. So if let's say your normal is good rainfall, is rainfall that is adequate for planting. Then in that case, you might then decide to spread your the types of seed that you are distributing or providing to farmers with advising farmers to provide plant a higher proportion to good yielding varieties, but you also plant a significant portion as well to more drought tolerant and typically lower yielding varieties or crops, because we're also expecting that there's a good chance of below normal rainfall. This is as a scenario based on the 2013 forecast. So I think that's what I wanted. This is really, I think, the most important, given kind of what we are going into in terms of the SACOF. The next few slides are a little bit more technical, and they try to illustrate, what is meant, what a dynamical forecast is, and the statistical forecast and so on. So I won't go into them in detail. Maybe I'll touch a few points here and there just for your understanding, but I know that the main interest of people here, or I think the main interest for people on this call is the application. Where can I get the data? Maybe to get a bit of understanding of the forecasts, but where can I get the forecast and the information and so on. So this is just to mention, remember I mentioned that, the dynamical forecast, this is an overview of dynamical forecasts. I mentioned that, they use equations to try and predict what will happen to a particular cell. And these are the kind of equations. So I guess we won't get much into them. I don't understand them either. So if that's any comfort, but the idea being to say that, there's a lot of mathematical computations that go on, and typically they use supercomputers to derive this sort of information. Yeah, and it basically is simulating the whole process of the what do you call it? The water, the water, global water balance, from evaporation, from some bodies. Okay, I said I wouldn't spend much time on it, so let me keep my promise. This is an example of dynamical forecasts. This is one of the forecasts that we use as well. It's called the C3S. It's a combination of forecasts from different centers, I think, and including the European Center. That's what ECEFO stands for, European Center for Medium Range Weather Forecasts, I think it is. And it's showing the same kind of thing. I think this has been expressed as a categorical forecast because they're giving specific rainfall amounts. So there's tends to be, some discussion in terms of, is it better to use a dynamical forecast or statistical forecast? There are benefits and drawbacks both ways. Benefits being that, we can clearly lay out how confident or uncertain we are in the forecast using some of the techniques. And the drawbacks being that, some physical processes are not simulated that well, partly because we don't know as a science community, it's still weather science is still a field of much discovery, because there's so much that still needs to be learned. But there's a lot of progress which has been made over the last few years and decades. The forecast models are constantly improving. So that's another advantage, I suppose, of dynamical forecast. We're getting to understand the processes better, and so our forecasts get better. Excuse me. Let's talk about statistical forecasts. I mentioned already that it's basically a relationship between a predictor, which can be like your sea surface temperatures, and a predictant, or if you want an outcome, which can be like the rainfall. And we do a statistical relationship, like a regression, to understand what the outcome would be. And so this is, I'm going to skip this, if that's okay. But all I meant to say is that, it's just finding a relationship between two different variables. And normally the variables are lagged. So when I say lagged, I mean that we can look at sea surface temperatures, for example, in July or August, and see how do they relate with rainfall in October to December. So you've got the information already now in terms of what is the sea surface temperatures over the Indian Ocean, which affects rainfall in Southern Africa. We've got information on it already for July or August, and we can use this to predict what rainfall will be like in October to December. So you can have those lagged, like with a time lag between the predictor and the predictant. So some of the benefits is that you can make specific forecasts with it. You can also use it with actual weather, like actual observations. Like I just gave the example of using sea surface temperatures, observed sea surface temperatures, to estimate rainfall or to predict rainfall. And the drawbacks is that is to an extent, some of it can be like what you call a black box system, being that you don't really, you just put something in and you get outputs out of it. That's not necessarily a bad thing, by the way, but because we know that there's relationships there, depending also how we define the predictors that we're using. And also, it's not based upon physical laws. Is one of the disadvantages. It doesn't account for other factors that we didn't necessarily include in our predictors. Quickly touching on analog forecasts. And these are basically, we say, for example, which year in the past looks like this year based on our predictors. So we might use El Nino Southern Oscillation as a predictor. Or for this year, for example, we're expecting a La Nina, right? For the 2022-2023 season. So we can select analog years and say which years in the past were La Nina years. And then we use these as our analog years. And then we look at last year was a La Nina, maybe 2017 might have been a La Nina, maybe 2005 might have been a La Nina. And so now we go back to our database and we pull out all those years. And then we say, okay, based on our analog years, we expect this year to be like one of these years or somewhere in a range of these years. That's what the analog approach looks like, based on, because we know that we're expecting a La Nina this year. Okay, so that's an example of how the analog forecasts work. There are also benefits and drawbacks to that. We're coming to the top of the hour. I haven't shown you any way to get the websites yet, so I'm going to skip some of this stuff and talk about the ensemble. With the ensemble, remember I mentioned that it's like basically we're running our dynamical forecast several times over. And when we do that, we get a different ranges. So this is a good example of what our dynamical forecast would look like. This is a forecast for La Nina, for the Nino 3. Okay, for the El Nino Southern Oscillation. Okay, the area in the ocean that we analyze or monitor El Nino and La Nina for. So in this particular case, we had observations for October, December, January, February, I think up to February. That's why these are observations based on actually recorded sea surface temperatures. And then from there, we're now running our models out several times. Remember, we said we just tweak our observations a little bit, our initial conditions, and say, okay, our observed sea surface temperatures was minus 0.9. Okay, so we put in the model, what if it was minus 0.91? And then you run out the model. Minus 0.92, run out the model again. And you do that several times. You do it for different models. This is one model, which is in the blue, another model, which is in orange. So each model is run out several times. When you do all of that and you analyze the results together, that's what we call an ensemble forecast. And you can see that by the time we get to October, we are not sure anymore whether it will be El Nino. If it's El Nino, it's below minus 0.5, right? But it's most likely going to be, most of the models are predicting that it will be between plus 0.5 and minus 0.5, which is taken as an neutral, ENSO neutral. So we can say that based on our ensemble, we're expecting probably ENSO neutral conditions, right? Although it's kind of, you can see it's edging towards La Nina. So that's the idea, but this whole range also gives you an idea of how confident you are in your forecast. So that's why we do that ensemble. Let's skip a few slides. And this is now the typical type of forecast that we get with when we do this. This is the NMME. It's one of the models that we typically use for analyzing what the forecasts could be like. Remember this graphic with the below normal probabilities, and above normal probabilities. Yeah, this was for 2017. And so the idea, this is to show that this is also an ensemble forecast, because NMME stands for North American Multi-Model Ensemble. So it's, I think it's derived from North American prediction centers. It's multiple models, and then you do an ensemble. And based on that ensemble, you run it several times, and you see how many times did our models, our ensemble predict below normal, how many times did our ensembles predict normal, how many times did our ensembles predict above normal, and then we come up with the probability based on those, the number of times that each model brings an output. These are this I can share with you. These are the websites where you can access our dynamical forecast. And typically we at FuseNet, we look at the NMME, which I've mentioned already. We look at the C3S as well. We can also look at IRI, which is from the University of Columbia. I think that's International Research Institute. Is also one of the, I think it's one of the WMO recognized centers. And then there's WMO is also doing its own forecast as well now, which is basically a combination of models from different centers. So you can click through these and you'll see the different models and interpret them based on all that. Okay, let's do some skipping now. And I think we've seen this already, Climate Outlook Forum example. And I'm going to switch now because the other aspect was seasonal monitoring. And now with seasonal monitoring, so far we've been talking about the forecast, right? But now we want to look at monitoring the season. What data sets can we use to see what has it actually rained or not? What is the vegetation like? Are we in drought conditions or stuff like that? So we've got a few products that we typically look at, which includes vegetation product, rainfall products, WRSI, and which is the water satisfaction index. It's a crop condition indicator. And we've got also evapotranspiration, which also is a crop condition indicator. And as I mentioned, this is the FuseNet experience. So these are just some of the products that we typically monitor in FuseNet to help us make predictions about or projections of what our end of season conditions will be like. And this is the website where you get access some of these products, the different products I mentioned. There's some that I didn't mention even in that, including like soil moisture estimates and others. The rest I mentioned. This is an example of the crop index that I mentioned. It's called the Water Requirement Satisfaction Index. And it basically tells us whether crops got enough water or they didn't. And then we also have rainfall. This is the website where we get our rainfall data for monitoring. And when we're doing this, we're seeing how much rainfall is estimated to have fallen and what is that rainfall as a percent of average. So is the rainfall above normal or below normal? So this is the estimate for last year. We've got vegetation as well, in which vegetation index, which tells us whether our vegetation is performing well or poorly. Yeah, so I think that's what I'll share with you. This is okay. So this is also evapotranspiration. Yeah. So I'm sorry, it's been probably quite a bit of a lot of packed information. I did try and cover the asks that had been given, which are to look at better understanding climate forecasts, where to get them, how to interpret them, which does require a bit of understanding of how the forecasts are derived, as well as seasonal monitoring data, which I didn't spend too much time on, but I believe that I think Curatia is going to be organizing a different different session for this as well in the future. So on that note, thank you. I'll be happy to take any questions or hand back to you, Curatia.
Thank you, Tamuka. Thanks for that excellent presentation. Lots of interesting information and background covered there. So that gives quite a bit of context to the forecast that we usually have a look at. Let me just open the floor and see if there's any questions. Would anybody like to ask Tamuka a question in the remaining 5 minutes we have? Okay, I see Gabriel. Gabriel's hand is up for now. Gabriel, go ahead.
Yeah, thanks, Curatia. Thank you so much, Tamuka, for the really good presentation. So one of the things we're trying to do right now is we've got what we call drought monitoring protocol within as a part of the activities that some of my colleagues are doing here at FAO. And what we hope to do is to kind of translate that protocol into the current format in which it is now, to try and scale it up to cover more areas. Now, my interest is really using some of the data sets that you've mentioned here to kind of do some of these analysis. I'm sorry if you already mentioned this, but would it be possible to kind of point us to where we could get some, like say, if I'm looking for the NDVI that I want to use for further analysis, if I'm looking for SPI that I might want to use for kind of much more further analysis, would you be having that kind of information that we can then get to use in our application? So just kind of give a background. What we're hoping to do is to write some kind of a code that would then fish some of this data and put them through some kind of analysis and get a product from that. So that's what we're hoping to do. Thank you so much. Over.
Okay, sure. That's a great question. Thank you very much, Gabriel. So I've put one of the websites here. This is where you can get like rainfall data and various derivatives of rainfall. And I can, please send me an email. I can give you the precise links. But yeah, you can actually link this up, but there are specific folders on this website where you can, pull the data sets directly and then, process them and so on. And then this is the other website as well, where you can download some of these, not just the pictures, but also the data like the NDVI. You can pull it directly from there. And you can also set up your system so that, you are pulling the actual data directly, because this website has been set up to make it easier for viewing and monitoring, just, for visual analysis and interpretation. But you do have a back end on this where you can pull your data directly into your system for processing. So send me an email. I can share you the precise links if I know exactly what you're looking for. Over.
Thank you so much. Thank you.
Okay.
Thanks,
Pleasure.
Tamuka. Let's see if there are any more hands. I don't see any more hands, Tamuka, but will you please share the presentation with us? And then we can send it out to people who've attended this this webinar. And I do think there's quite a bit of interest, Tamuka, if you would be interested in just having a follow-up webinar only on the indicators that you have mentioned, zoning in on the WRSI and NDVI, other information that is available from FuseNet that we can use for drought and dry spells, particularly monitoring them and, interpreting them for programming. But let's see if there's further interest in that also from partners. And yeah, and then we can schedule something perhaps next month.
Okay, yeah, I think we can work that out in terms of the feasibility. Yeah, I think as we discuss further.
Okay. So on that note, then I would say thank you so much. There's no more questions. We have 1 more minute. If anybody wants to add anything quickly, or questions quickly. No, just applause for you, Tamuka. Lots of applause for you. So thank you so much. It's been very insightful, and we've all learned quite a bit of new information on how these forecasts are generated and the background to it. So thank you so much. And thank you everyone for attending as well. And if you have any questions, if you'd like to see any particular climate webinar, because I didn't mention in the beginning, but the FNSWG wants to create, a series of climate webinars. So we've started off with this one, a contextual background to forecasts and different types of forecasts. We will also have one on dry spells and drought. We will have on floods, cyclones, and early warning indicators for those hazards as well coming up during the rest of the months for the year. But if you want to see anything in particular, please pop Selam an email, and we will definitely work on setting that up for you. So thank you so much, everyone. Have a great day. Bye for now.
Thank you so much. Okay, bye.